Hello and welcome to Bay College's online lectures for intermediate algebra. Today we're going to be looking at common and natural logs. The first one we're going to look at is base 10. Now base 10 is called our common log, and the reason why it's called our common log is essentially because our number system is based on the factors of 10. If you think about, if we multiply something by 10, essentially we add a 0 or move the decimal place to the right. If we divide by a factor of 10, we move the decimal place to the left one spot. So that's our decimal system. It's based on factors of 10. So when we deal with common logs, it's so common because it's the basis of our number system, we call it the common log. So when we see something like log base 10 of x, it's so common that we actually write it as log x. Just like anything that has a coefficient of 1, we don't write 1. Well, whenever we have a logarithm with base 10, we don't write it. We assume that it is the common log. So whenever you see log of x without the denotion of any base, you know it's a common log. So if we look at common logs, and we should be somewhat familiar with our own number system, log of 100. Well, this is saying log base 10. And if we recall it from the previous section, what does a log ask us? It says 10, our base, to what power is 100? Well, this is something we should be able to intuitively figure out. Well, 10 to the second power, 10 times 10, is 100. So this value is log of 100 is 2. If we look at this one, well, how many factors of 10 do we have here? 10 to what power is 1,000? That's what the log asks us. Well, that would be 3. 10 times 10 is 100, times another 10 would be 1,000. If we look at this, well, this is going the other way, right? If we think about 10 to what power is 0.01? Well, 1/10 would be the first value after the decimal. 1/100th, and that's how we read this, well, 1/100th would be dividing by 2 factors of 10. And if we remember our rules of exponents, our exponent would be -2. 10 to the negative second power is 1 over 100, or 1/100th, converting a fraction to a decimal. But what if we don't have things that are real nice factors of 10? What if we have something like this, log of 500? Well, we can do a little bit of estimating. This value is more than 100, but less than 1,000. So it's more than a value of 2, but less than a value of 3. This is where we need to use a calculator in intermediate algebra. I know I haven't said that too much in these lectures, but this is where we need a calculator. There are very few people on earth who can just do logarithms in their head unless they're nice, easy logarithms. This is not. This is something that we have to put in our calculator. So at this point, pull out your calculator and follow along with me. If we actually find the log key on our scientific or graphing calculator, we can hit that and enter 500 and then hit equals. And we'll get a decimal equivalent that eventually has to round to some point. This is an irrational number. So we're going to get 2.69, and I wrote it on the board over there because I don't have a calculator handy, but this is an estimate. I have to approximate, I have to round to some point, and this is the value I'm rounding to. What if we have numbers like log of 242? Well, 10 to what power is 242? Again, it's a value that's going to be more than 2 because 10 squared is 100. This is more than 100. So if we approximate that using a calculator and we end up rounding it, we're going to get 2.38382 if we round to that decimal point there. So you can see, yeah, that's a value greater than 2, but less than 3, because this isn't 1,000. Same here. So we can have an idea if we just estimate it. So when we plug it into our calculators and we get a value like this, we can pretty much trust that we typed it into the calculator correctly and we didn't make something called, like I like to call, a fat-fingered mistake. Sometimes we do those with calculators. Now we're going to kind of review using logs base 10s of our rules of logarithms. Log of 1. Well, regardless of the base, it's always 0 because anything to the 0 power is 1. Whenever we take the log of 1, regardless of the base, we get 0. Well, what about log of 0? 10 to what power is 0? Well, there is no power that makes 10 0. Okay? This is undefined. And if we recall when we talked about domain of logarithmic functions or even exponential functions, there are domain restrictions, right? X has to be greater than 0, while what we're plugging in is 0, so it's undefined. And if the domain of any logarithm is greater than 0, this tells me we're going to get an error when we plug it into our calculator. So if you're working along at home, plug it into your calculator and see what it says. It might say domain error or just error altogether. So this is not within our domain. So maybe our calculator says error. If only I could spell. All right, let's look at utilizing a logarithm here. What do we do here? What are we asked to find when we're given log x? Well, we know the base is 10. We make that assumption. Logarithms are always equal to power. So what this is asking me is if I write it as an exponential equation, my base is 10, my power is 4, I can then solve for x. 10 to the 4th power is 10,000. So we've solved that. But what about this? Again, this is an application where we need a calculator. If we rewrite it as an exponential equation, 10 to the 2.2. Well, if we recall what we did back there, I know this is going to be a value greater than 100, but less than 1,000, because this is a value of power greater than 2, but less than 3. And if we plug that into our calculator, we're going to get 158.48932. And again, I shouldn't even have an equal sign here. What I should have is an approximation. Okay? And again, it's greater than 100, but less than 1,000. 2.2 is our power. So we can say, okay, that's approximately what it's equal to. We have to round it to some point. And that's one of the drawbacks of working with a calculator. We can't leave it in exact form every single time. So that's our base 10 logarithms, our common logs. Well, here we have base e. This is a very frequent base when it comes to economics or biology. Maybe we're talking about bacterial growth. They grow at a base of e, which is interesting that this number appears in nature. We've talked about e in previous sections, but now we're actually going to look at the natural log, the log of the natural number. Well, it's sometimes denoted, or actually mostly denoted, as ln of x. This means base e. So when we see ln, we recognize it as base e. And you can also find that key on your calculator. The interesting thing about our calculators is they can only do directly two types of logarithms, our base 10, our common log, or our natural log. And this is called the natural log. Now the reason why it's ln is because it was discovered and published by a French mathematician, so it's actually log naturel. But either way, ln, it means base e. So if we have something like this, ln of 4, well, this is something, when we have a base that's an irrational number, chances are we're going to get values that are irrational numbers. So this, again, is something, be familiar with your calculator, know where this key is, know how to use it, and plug it in. So if we plug ln of 4 into our calculator, we're going to get 1.38629. And just for estimating purposes, we know e is a little bit more than 2.1878, whatever, right? And if we're raising it to some power to get 4, well, we're not squaring it, but it's more than 1. Otherwise, it would just be e. And this value is not e. ln of 18, well, we know that's a value that's going to be greater than squaring e. Or maybe we don't, but we can use our calculators. We can plug it in. ln of 18 is going to give us an approximation of 289,037. And again, that's an approximation because we do have to round it. If you're following along in your calculators, when you plug this in, you're going to get something that maybe even has more decimals. We have to round it at some point. The calculator does round it because it can't display an infinite numbers. What about ln of e? Well, what is this asking me? It's saying e to what power is e? Well, e to the first power is e. So we can see our properties of log still hold true here. ln of 1, well, e to what power is 1? Well, we know any base to the power of 0 is 1. So that's like that's our x-intercept if we were to graph ln of x. ln of 0, well, if we recall, when it comes to logarithms, this isn't in our domain. If we plug this into our calculator, again, we're going to get that undefined. And I'm just going to abbreviate UND. If we try ln of -4, if you put this in your calculator, it's going to say there's a domain restriction, or it's just going to tell you there's an error. So all of our properties of logarithms still apply. We're just looking at two special logs, one that's base 10 and one that's base e. So what can we do to solve natural logs? Well, if we take a look at this, essentially let's rewrite it as an exponential equation. I know my base is e, which is an irrational number like pi, 2.17828, whatever. And my power is 5, so e to the 5th. Well, I can put that into my calculator because on the same key, whether it's scientific or graphing, you might have to hit the shift to access the e to whatever power. So we hit that key and we put in the value 5, and we can approximate it, we have over here, to 148.41316. And again, this is an approximation because we do have to round it to some point. So this is essentially our basis of base 10, our common logs, and base e, our natural logs, which you'll see occur a lot in many of the sciences. One example of common logs would be pH. Maybe you're in a chemistry class and you've got to calculate pH. That's all done on a base 10 system. Or maybe you're in a biology class and you have to deal with bacteria growth, or maybe cooling and heating curves in some other class, maybe physics. You'll end up dealing with base E. So this has been section 8.6. Thank you for watching.